Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to use our knowledge of electrochemistry to do a quick overview of energy producing technology such as batteries and fuel cells. So really, when we're looking at batteries and fuel cells, these are just different types of galvanic and electrolytic cells, sometimes individually and sometimes combined. And one of the big things to keep in mind about a lot of these cells is these are really just energy storage methods, where I can store energy as a chemical structure, which I can then pull out electricity in the form of potential and current that I can then use. So the simplest form of battery we can look at is called a primary cell. So what this is just a galvanic cell. I go ahead and I hook it up. It will create a positive potential, which I can use to generate a reaction, but it can't be recharged. It only really goes forward in one direction. So we've already seen one form of this with the voltaic pile. So this is really the world's first battery, where we combine copper solids and zincs to form copper solid and zinc ions. And again, this had a potential of 1.1 volts, where we are taking a zinc anode and then hooking up to a copper cathode. And again, just changing out who's in solution. However, one of the big problems with a lot of these early batteries is you'll note that we have a reliance on the potential with both the concentration of zinc and copper ions, and these will change with time. So this means that the potential for a voltaic pile will fluctuate up and down with the concentrations of the individual ions, which, is fine for original applications. However, if you tried to run a fluctuating potential through your phone, wouldn't end so well. And so a lot of the modern batteries try and go ahead and compensate this by using some advanced techniques. So one of the modern primary cell batteries is called a silver zinc button battery. So you've probably seen this in any number of electronics. These are fairly popular because of their relatively small size and high amount of charge that they can hold. So in this case, what we have is the oxidation of zinc solid to a zinc oxide instead of just zinc ions. And this is essentially driven under basic conditions by the presence of hydroxide. On the other hand, our reduction reaction is going to be taking silver oxide, so again, solid instead of ions, combining it with water to generate hydroxide, and again, consuming 2 electrons. When you combine these 2 reactions together, we have an overall cell potential of 1.8 volts, which is fairly high and quite respectable. This will drive a lot of different processes. But one of the more notable features when you take a look at this reaction is the phase of all the species: solid, 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 solid. So if I go ahead and hook this up, what I'm going to have is I'm going to have a zinc anode. So again, this will be solid zinc. And then I'll have, which then connects to a zinc electrolyte. So this will essentially be a paste of zinc oxide, which is then connected to a paste of silver oxide, and then finally hooked up to a silver cathode. And as we go from zinc to cathode, it has to go through all these solid or mixed pastes. But one of the cool features about this as you go through is you'll note that every single phase, even this potassium hydroxide, which is blended into that paste, is solid. So we've got no production or consumption of any aqueous phase species or gas phase species. This means that all of our concentrations stay relatively constant, which means the Nernst equation doesn't really play a role. There is no Q. The Q of this reaction is 1. It will produce a constant 1.8 volts. It won't really fluctuate. And this is one of the reasons why, if say you have a battery, or sorry, you have a watch, the battery essentially holds steady. The watch works pretty well right up until it suddenly dies. It doesn't dim out. And one of the reasons why is because this potential stays relatively fixed until we finally started to consume enough of either our silver oxide or our zinc solid that there isn't reliably one or the other, and so that potential can't flow quite so well. And again, This is aided by the fact that we have solids, and even our hydroxide, which should be aqueous, is usually blended into a paste to keep that concentration relatively constant. And this is also one of the reasons why, if you have a broken or ruptured battery, you often don't want to end up touching the substance that comes out, because it's usually a sodium hydroxide or potassium hydroxide paste, which it can be quite caustic and leave those chemical burns on your hands. But one of the unfortunate part about all these primary cells is that they only run in one direction. If I try to apply a potential to this reaction to drive it in reverse, all of these primary batteries either have such a high overpotential in the reverse direction that it's impractical to recharge them, or if I tried to reform my reactants, that silver oxide wouldn't form in the right location, or the zinc solid would again form over here, and so it wouldn't participate as part of the anode. Essentially, there's a lot of physical complications that don't allow for a nice, easy back reaction. However, there are plenty of modern batteries that are rechargeable. And this means it can be run not only as a galvanic cell producing energy, but as an electrolytic cell where it consumes energy to reform your reactants. So these are known as secondary cells. They can go forwards or backwards. The most common modern rechargeable battery is going to be the lithium-ion battery. So this one couples really kind of a fun oxidation reaction where you take a lithium cobalt oxide, which releases an electron by essentially pulling off the lithium as a lithium ion and as an electron. That electron then creates this current, which goes over to the cathode, which in this case is a lithium carbide. And the lithium floats through an electrolyte to again recombine with a solid carbon electrode to essentially form that lithium carbide. When you pair together these two half reactions, the net reaction has a cell potential of 3.6 volts, which, let's be honest, is a lot of energy compared to a lot of the other reactions we've seen. Now let's go ahead and take a look at what the system would actually look like. So again, we'd start with that cathode, or we start with our anode, which is essentially producing, which is undergoing oxidation. And it will be hooked up to this lithium carbide. So the lithium carbide is essentially this combination of a solid graphene sheets. So again, nice carbon with lithium ions that essentially go ahead and sit in between and help support extra electrons building up on this sheet. Then we have essentially this electrolyte where lithium ions are allowed to float from one side to another. And then we have this lithium metal, usually cobalt oxides. So again, the more lithium you have present in either your oxide or your graphite, the more electrons can be present. So really what we're doing is allowing the lithium to move from side to side. And because the electrons won't flow with it through the porous separator, they have to go the long ways through through a circuit where we can go ahead and use this energy. And because you'll notice, since all we're doing is moving lithium ions from side to side, it's very easy to run this reaction either forwards or in reverse. So it is quite a cool reaction. However, batteries aren't the only way to store and produce energy. One of the other cool techniques that is very chemical in nature is called a fuel cell. So fuel cells, what they do is they obtain their electrical energy by running an electrochemical reaction that will produce a steady source of electrons by essentially flowing in a flow of fuels, often liquids or gases, to both a cathode and an anode to allow for a constant reaction. So again, these are referred to as fuel cells because we're really putting in a fuel to drive the reaction and not just using solids like in batteries. So one of the most widely used types is called the hydrogen fuel cell. And this should look fairly familiar as it's just the reverse of our water splitting reaction. In this case, we're oxidizing hydrogen. And again, this has a reduction potential of 0 volts. And we're now, instead of oxidizing water, we're reducing oxygen using those extra protons and electrons produced by the hydrogen to form the water. And this has a potential of 1.23 volts. Now, in this case, because our reduction reaction has the 1.23 volts, we subtract out our hydrogen electrode, which is 0, and we end up with a water forming reaction of 1.23 volts. So you'll note that this actually works a lot like combustion of hydrogen. I add hydrogen and oxygen, and I produce water. However, it turns out that this produces an energy a lot more efficiently than just simply burning hydrogen would. So what we can do in this case is we can add in our fuel, in this case, hydrogen, to the anode. So the hydrogen comes in, reacts on the anode. So it breaks apart into protons and electrons. The electrons go through a motor to go over to the cathode. Meanwhile, the protons flow through an electrolyte, again, very similar to what we saw lithium doing through a solid separator, to the cathode. At this point, they can go ahead and recombine with the oxygen that's being fed into the cathode and produces water as a byproduct. So again, this is a very green reaction. We're feeding in hydrogen, which can be produced from water, and oxygen, which is available in the environment, and we produce water as a fairly clean product. So in a lot of senses, a fuel cell in its most ideal form can run a lot like a battery. But instead of storing it in solids, we're storing it in liquids that are more easy to liquids and gases that are more easy to transport. And it is worth noting that fuel cells aren't just an idea of the future, they have actually started to see real use. And there are several hydrogen fuel cell vehicles that are currently being produced. Noticeably, this is the Toyota Mirai on top and the Hyundai Nexo on bottom. And it's worth noting, while these are still fairly new and expensive, the Mirai is actually down to a starting cost of about $50,000, while the Nexo, not unreasonably for an SUV, is about $60,000. So while still out of the price range of a lot of modern consumers and the difficulty of finding hydrogen fueling stations, they are a potential vehicle of the future. And as long as the hydrogen comes from a renewable source, like the electrolysis of water, it is a lot of possibilities for the future. And it is worth noting that in addition to the classic hydrogen fuel cell, a lot of other fuel cells have come under investigation, including using methanol, phosphoric acid, and a lot of other species. So next time, we're going to go ahead and look at what happens when redox reactions go wrong and try and use electrochemistry to explain corrosion effects. Until then, take care.